minus 2 root 2. We'll just leave that as the same. Now we can divide through by 2 and we get root 6 minus root 2, which is what we have to prove. So that completes the second part. Now I've got to do the first part, which shows you that the triangle must be this triangle in order to have the longest shortest side. Okay, I've drawn some squares here. I suspect there might be a very short and slick way of showing this, but I don't know a short slick way, so I'll show you a slower way. What I'm trying to do is to show that the triangle with the longest shortest side must be an equilateral triangle with one of the corners in the corner of the square. So I'm going to work at that in stages. First of all, I'm going to show that the corner of the triangle must be in the corner of the square. And I'm going to show this by an argument called reductio ad absurdum. That is, I'm going to assume the opposite and show that, that we reach some contradiction. So I want to assume that there is a triangle, and I'll just draw a triangle here, where none of the sides are in the corner. I'll call the triangle PQR, and I'll call the lengths of the sides P, small q, and small r. And I want to assume that a triangle like this is in fact the triangle with the longest shortest side. So PQ and R are bigger than, or at least the smallest of PQ and R is bigger than any other triangle which you can fit in this way. And then we'll show that there's a contradiction. And we can reach the contradiction in the following way. Notice that if these 3 points are not on a corner, there must be one side, in this case AD, which doesn't have any point on it. And what I want to do here is I want to show, let's take the point P, and suppose I slide P towards A. Don't have to slide it very much, just want to slide P towards A in that direction. And if you do that, notice that R and Q both increase. Then I want to slide the line PR towards the line AD. Okay, so I'm sliding PR uniformly down so that Q remains the same length, but R and P get bigger. So I'm sliding PR towards the line AD, and that means that R and P increase. And let's suppose I do, there's a little bit of space here, so let's suppose I do a little bit of both of those. If I do a little bit of both of those, then P, Q, and R all increase. And what that means is that the triangle PQR was not optimal in the way that we described. That is, it wasn't the triangle whose shortest sides was as long as it could be, because if we go through this little procedure here that I've just described, you can make every side bigger. So we have a contradiction, and that's what we call a reductio ad absurdum. That means that the triangle with the longest shortest side can't be like this. It must have one of the points coinciding with a corner, which we might as well make A. Right, we've shown that the triangle we're looking for must have a corner which coincides with the corner of the square. Now let's deal with some other cases, and now I want to assume that this is the triangle which has the property we're looking for, and I want to assume that one of P, Q and R is smaller than the others. And if that's the case, I've drawn roughly the triangle here, so P, Q and R is smallest. And I just want to show that if we slide Q towards R, towards C, then if R was the smallest, R would get bigger. On the other hand, if P was the smallest, if we slide Q in the opposite direction, then P will get bigger. Now, of course, R is getting smaller, but P can get a little bit bigger while still being smaller than R. Similarly, if it's Q, which is the smallest, we can move R down the way, in which case Q will get a little bit smaller, and we can move up the way, then Q will get a little bit bigger. So we can, by sliding Q or R, we can make, we can make a bigger triangle. And that will again contradict the fact that this was the best triangle to start with. Well, finally, I want to deal with the case that PQR is an isosceles triangle where the two equal sides are shorter than the other. So we've started off, first of all, we have shown that one of the corners must coincide with the corner of the square. Then we said, well, if there's a smallest side, that's not going to work because we can slide various of the points along the square and make the whole triangle bigger. The only other case is that it's an isosceles triangle, and there's two kinds. In this upper one here, we have the longest side being QR, and in this case, if you slide the whole side, well, we slide Q towards C and R towards C in such a way that it remains an isosceles triangle, then R gets smaller and P, both P's get bigger, and the whole triangle therefore gets bigger. And intuitively you can see that that will stop happening when you get an equilateral triangle, which is the one that we were actually wanting to show occurred. And in the bottom case it's nearly the same, except that QR has to slide round. So Q has to move this way and R has to move this way in such a way that it remains an isosceles triangle. So P again gets bigger and R smaller, and you contradict the fact that this was the optimal triangle in the first place. So maybe there's a shorter way of doing this, but you can see by treating these cases that the best triangle is the one which is equilateral and has a corner coinciding with a corner of the square, and that's what we assumed to begin with and proved the thing we were asked to prove. So that's the end of this presentation. That's all for now.